All right, let's explore. Number 10. Shadow matter, the invisible universe next door. In 1984, four physicists at Princeton University published a paper that quietly rewrote our understanding of what the universe actually contains. David Gross, Jeffrey Harvey, Emil Martinec, and Ryan Rohm, working on what became known as heterotic string theory, proposed that reality requires not 4 dimensions, but 26, and that most of what exists in our universe is permanently invisible to us. At the time, the dominant question in physics was why roughly 27% of the universe's total mass appeared to exert gravitational force without emitting, absorbing, or reflecting any light. Astronomers had been measuring this invisible mass since the 1930s, when Fritz Zwicky first noticed that galaxy clusters were behaving as though they contained far more matter than anyone could see. The working assumption was that the missing mass was simply ordinary matter we hadn't detected yet. Heterotic string theory suggested something far stranger. The mathematics required the existence of a parallel sector of matter, physically occupying the same space as our world, but existing in dimensional states our instruments are constitutionally incapable of registering. Physicists called it shadow matter. In 1985, Edward Kolb, David Seckel, and Michael Turner published a paper in Physical Review Letters formally proposing shadow matter as a candidate for the missing mass in the universe. Shadow matter would have mass, it would interact gravitationally, and it would follow the same fundamental rules as ordinary matter. That means it could, in principle, form clouds, collapse under gravity, and coalesce into structures. Shadow stars, shadow planets, shadow chemistry, all of it invisible, all of it right here, occupying the same space you're sitting in right now. What makes this theory genuinely unsettling is not the mathematics, it is the implication. If shadow matter forms structures, there may be an entire shadow universe interpenetrating ours, and we would have no way of knowing what it contains. Number 9. The Kaluza-Klein Tower, where gravity goes when it leaves our world. In 1919, a virtually unknown German mathematician named Theodor Kaluza sent Albert Einstein a paper so strange that Einstein sat on it for 2 full years before he could decide whether to publish it. Kaluza had taken Einstein's own equations of general relativity and solved them in 5 dimensions instead of 4. The extra dimension produced, without any forcing or manipulation, a perfect mathematical description of electromagnetism. Einstein was simultaneously fascinated and disturbed. The theory should have solved an enormous problem immediately. Gravity is catastrophically weak compared to every other fundamental force in nature. A small magnet can lift a paperclip against the gravitational pull of an entire planet. When physicists calculate how weak gravity actually is relative to electromagnetism, the difference is staggering, more than 1 trillion times weaker. A disparity so extreme it is called the hierarchy problem, and it has no solution within standard physics. Kaluza's insight, refined in 1926 by Swedish physicist Oskar Klein, who proposed that the extra dimension was curled up at scales near the Planck length of approximately 1.616 times 10 to the negative 35 meters, offered a startling explanation. Gravity is not actually weak. Gravity is full strength, but it bleeds into the extra dimension, diluting itself across a space we cannot access. And what we experience as gravity is only the fraction that remains in our 3-dimensional world. Since 1999, physicists at CERN's Large Hadron Collider have been searching for the experimental signature of this process, specifically particles called Kaluza-Klein gravitons, which would represent gravitational energy that briefly escaped into the extra dimension before returning to ours. As of 2024, none have been confirmed. Every time you watch an object fall to the ground, you may be watching a force that is, in reality, vastly more powerful than it appears, diminished because most of it is escaping somewhere we have never been able to point. Number 8. The bulk. the hyperdimensional ocean. Our universe floats in. In 1999, two physicists published back-to-back papers that forced cosmologists to consider a possibility most had treated as science fiction. Our entire universe, every galaxy, every star, every particle of matter that has ever existed is a thin three-dimensional membrane floating inside a higher dimensional space of almost unimaginable scale. The physicists were Lisa Randall, then at the Massachusetts Institute of Technology, and Raman Sundram. The higher dimensional space they described had a name. They called it the bulk. Before Randall and Sundram, extra dimensions in physics were typically assumed to be small, compact, and curled up at scales far below anything measurable. The prevailing picture was that extra dimensions existed but were essentially irrelevant to the large-scale structure of the universe. The Randall-Sundram models, published in Physical Review letters, proposed something fundamentally different. At least one extra dimension could be effectively infinite in extent. In their framework, our universe is what physicists call a three-brane, a three-dimensional membrane embedded in a five-dimensional anti-de Sitter space. The particles and forces that make up everything we can observe, light, matter, electromagnetism, the strong and weak nuclear forces, are all confined to our membrane. They cannot leave. But gravity is different. Gravity propagates through the bulk itself, which is why we feel it, and why it behaves as though it comes from everywhere. The Randall-Sundram models also elegantly resolve the hierarchy problem without requiring the kind of mathematical fine-tuning that had plagued previous attempts. The geometry of the bulk naturally suppresses the strength of gravity on our brain, producing exactly the weakness we observe. The solution to one of physics' deepest puzzles was hiding in a dimension outside our universe entirely. Our universe may not be all of reality. It may be an object, a membrane, floating inside something enormously larger, and whatever else is floating in that same bulk remains, for now, completely beyond our reach. Number 7, the ekpyrotic universe, where the Big Bang was a collision between dimensions. In 2001, cosmologists Paul Steinhardt of Princeton University and Neil Turok of Cambridge University published a paper in the journal Science that made many of their colleagues deeply uncomfortable. They proposed that the Big Bang, the event we treat as the absolute origin of space, time, and physical law, was not a beginning. It was an impact. Our universe was a membrane that collided with another membrane, moving through a higher dimensional space. And the heat and energy of that collision is what we experience as the birth of everything we know. The name they gave this model came from ancient Stoic philosophy. The Greek word ekpyrosis described the belief that the universe periodically destroyed itself in fire and was reborn from the ashes. Steinhardt and Turok chose the name deliberately. Their model predicted that the collision between membranes was not a one-time event, but a recurring one, playing out on timescales of trillions of years, a cosmic rhythm of destruction and renewal driven by the physics of extra-dimensional space. The standard model of cosmology requires the Big Bang to have originated from a singularity, a point of infinite density where all known physics breaks down and the equations produce meaningless results. The ekpyrotic model eliminates the singularity entirely. The collision between two membranes, separated in the extra dimension by approximately the Planck length, produces a hot, dense, expanding universe without ever requiring infinite density or a true beginning of time. The model makes specific predictions about the pattern of gravitational waves produced by such a collision, predictions that differ measurably from standard inflationary cosmology. The European Space Agency's LISA Observatory, currently planned for launch around 2035, may be able to distinguish between these signatures for the first time. The universe as we know it may not have been born. It may have been produced by a catastrophic dimensional collision that has happened before, and according to the mathematics, will happen again. Number 6. Dark energy as dimensional leakage, the force destroying our universe may come from outside it. In 1998, two independent teams of astronomers set out to measure how quickly the expansion of the universe was slowing down. They expected deceleration. Gravity pulls matter together, and the accumulated gravity of everything in the universe should have been putting the brakes on cosmic expansion since the Big Bang. The High Z supernova search team, led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, were both measuring distant supernovae to pin down the rate of that deceleration. What they found instead earned all three scientists the Nobel Prize in Physics in 2011. The expansion was not slowing down, it was accelerating. Something was pushing the universe apart with increasing force, overcoming the gravity of all the matter in existence, and driving galaxies away from each other at ever greater speeds. Physicists named this unknown force dark energy, and according to data from the European Space Agency's Planck satellite published in 2018, it constitutes approximately 68% of the total energy content of the universe. The leading theoretical candidate for dark energy is the energy of empty space itself, what physicists call the cosmological constant. But when quantum field theory calculates how strong this energy should be, the prediction is off by a factor of 10 to the power of 120. That is not a rounding error. It is widely described as the worst prediction in the history of physics, a discrepancy so vast it suggests the theory is missing something fundamental. In 2000, physicist Gia Dvali and colleagues proposed a striking alternative. At cosmic scales, gravity begins to leak into extra dimensions, diluting its attractive pull and allowing space to accelerate outward. The apparent dark energy we observe would be a side effect of gravity escaping through a dimensional boundary. The European Space Agency's Euclid telescope, launched in July 2023, is currently collecting data that may test whether dark energy's strength varies over cosmic time, which would distinguish between these explanations. The force that will ultimately determine the fate of everything in existence, accelerating the universe toward a cold and empty dissolution, may not originate in our universe at all, but may be leaking in from the dimensional structure surrounding it. Number 5. The fifth force, the anomaly that keeps appearing where extra dimensions should be. On January 6, 1986, physicist Ephraim Fishbach published a paper in Physical Review Letters that reopened one of the most carefully closed questions in science. Fishbach had been re-examining the meticulous torsion balance experiments conducted by Hungarian physicist Loránd Eötvös between 1889 and 1922, experiments that had become the gold standard for testing the universality of gravity. When Fishbach reanalyzed the data with fresh eyes and modern statistical methods, he found something Eötvös had not reported. The measurements contained systematic deviations that could not be explained by any of the four known fundamental forces. Physics recognizes exactly four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. This framework, the Standard Model, had been tested to extraordinary precision for decades. Extra dimensions, however, predict a clear experimental signature. At very small scales, where the influence of compactified extra dimensions becomes significant, gravity should deviate from the familiar inverse square law that Newton described in 1687. A new interaction, a fifth force, should appear precisely at those scales. The E. Wash Group at the University of Washington, one of the most respected precision measurement laboratories in the world, has tested gravitational behavior down to 52 micrometers, as reported in their 2007 paper in Physical Review Letters, and found no confirmed deviation. But anomalies have persisted elsewhere. In 2016, physicist Attila Krasznahorkai at the Hungarian Academy of Sciences reported an unexpected signal in beryllium-8 nuclear decay, a particle decaying in a way that required a new boson with a mass of approximately 17 million electron volts. The so-called X-17 particle, if real, could represent a new force operating in the range where extra-dimensional effects are predicted. As of 2024, experiments at CERN's Na-64 detector have neither confirmed nor definitively excluded it. We have been searching for the signature of extra dimensions for over a century. The anomalies appear, they resist confirmation, and they never entirely disappear. Something keeps showing up in exactly the places the equations say it should. Number 4. The holographic principle. Evidence that the third dimension may not be real. In 1993, Dutch physicist Gerard 't Hooft, who would go on to share the Nobel Prize in Physics in 1999, published a paper proposing something that sounded more like philosophy than physics. Every piece of information needed to describe the contents of a three-dimensional region of space. Every particle, every force, every interaction could be completely encoded on the two-dimensional surface surrounding that region. The three-dimensional interior was not the fundamental reality. The two-dimensional boundary was. The universe, 't Hooft was suggesting, might be a hologram. The idea had deep roots in the physics of black holes. Stephen Hawking and Jacob Bekenstein had shown in the 1970s that the information content of a black hole was proportional not to its volume, but to its surface area. This was profoundly counterintuitive. If you fill a box with information, you expect more information to require a bigger volume. But black holes appeared to store all their information on their outer surface, as though the interior were, in some sense, redundant. Physicist Leonard Susskind extended 't Hooft's work in 1995 and gave the framework its name, the holographic principle. In 1997, Argentine physicist Juan Maldacena provided what became the most cited paper in physics of the last 30 years. His AD-CFT correspondence demonstrated mathematically that a theory of gravity operating in three spatial dimensions is exactly equivalent to a quantum field theory operating on the two-dimensional boundary surrounding that space. Equivalent, not analogous, not similar. The same physics, described two different ways. This meant the dimension of depth, the experience of inside, of volume, of spatial extension in three directions, might be a derived property rather than a fundamental one. Fermilab operated an experiment called the holometer between 2014 and 2015, searching for quantum-scale pixelation that one specific holographic model predicted would manifest as correlated noise in precisely timed laser interferometers. The experiment found no evidence for that particular model. What no experiment has done is rule out the holographic principle itself, and the most rigorously supported framework in theoretical physics continues to suggest that the dimension you experience most viscerally, the dimension of depth and volume and physical space, may be a projection from a surface you will never reach. Number 3. Demons in the equations. What M-theory says is hiding in the other 7 dimensions. In March 1995, physicist Edward Whyton stood before an audience of the world's leading string theorists at the University of Southern California and announced that the 5 competing versions of string theory, each internally consistent, each making different predictions, were not rivals. They were all approximations of a single, deeper theory operating in 11 dimensions. Whyton called it M-theory. When his colleagues asked what the M stood for, he declined to say, suggesting the answer should be left for the future. The equations, however, were less coy about what those extra 7 dimensions actually contain. String theory, in all its variants, had already required the universe to have more dimensions than the 4 we experience. The standard picture proposed that the extra dimensions were compactified, folded into shapes so small that particles moving through them would have wavelengths too long to resolve the structure, rendering them effectively invisible. In the theories leading up to M-theory, these compact dimensions were described by 6-dimensional geometric objects called Calabi-Yau manifolds, shapes of extraordinary mathematical complexity with no real-world analogy. M-theory requires 7 additional compactified dimensions rather than 6, and the geometry of those dimensions is not decorative. It is functional. The specific shape of the compactified space directly determines the physical constants of our universe. The mass of the electron, the strength of the strong nuclear force, the ratio of matter to antimatter produced in the Big Bang. All of these are consequences of the geometric configuration of dimensions, too small to measure. A different folding would produce a universe with different particles, different forces, and different laws. Nothing we recognize as matter or life would exist. Physicist Leonard Susskind, developing the implications of M-theory, calculated that the number of possible geometric configurations of the compact dimensions is approximately 10 to the power of 500, each one corresponding to a different set of physical laws, a different universe with different contents. The laws of physics are not universal truths written into the nature of reality. They are the local consequences of a geometric shape folded into dimensions smaller than anything we can measure. And the shape that produced our universe is one of a near infinite number of alternatives hidden in the structure of space itself. Number 2. The many worlds membrane. Every decision you have ever made has created a dimension you will never reach. In 1956, a Princeton graduate student named Hugh Everett III submitted a doctoral thesis that his advisor, the legendary physicist John Archibald Wheeler, required him to drastically shorten before the university would accept it. The shortened version was published in Reviews of Modern Physics in 1957. What it proposed was so radical that the physics community largely ignored it for nearly 2 decades. Everett had read the equations of quantum mechanics with uncomfortable literalness and arrived at a conclusion that most of his colleagues preferred not to consider. Every quantum event that can have multiple outcomes does have multiple outcomes, simultaneously in branching dimensional realities that are each as physically real as the one we inhabit. Quantum mechanics, the most precisely tested theory in the history of science, describes particles not as objects with definite states, but as probability waves, existing in superpositions of multiple possibilities simultaneously. The standard Copenhagen interpretation resolves this by proposing that observation collapses the wave function, forcing the particle to choose a single outcome. Everett asked what the equations required if you took them at face value without inserting a collapse. The answer was that all outcomes occurred, each in a separate branch of reality, and the observer split along with them, with each version of the observer experiencing one outcome and having no access to the others. Physicist Bryce DeWitt popularized the framework in a 1970 article in Physics Today, giving it the name most people now use, the many worlds interpretation. Oxford physicist David Deutsch has argued since his 1985 paper in the Proceedings of the Royal Society that many worlds is not merely one interpretation among many, but the only interpretation that takes the Schrödinger equation seriously without adding external assumptions. A survey of physicists published in Studies in History and Philosophy of Modern Physics found it the second most popular interpretation of quantum mechanics among working physicists, behind only the Copenhagen interpretation it was designed to replace. The branching does not happen somewhere else. It happens inside every atom, in every interaction, continuously, producing new dimensional realities at a rate beyond any possible calculation. Each branch is real. The people in them are real. They have your memories up to the moment of divergence and no knowledge that you exist. Every choice you did not make, every path you did not take, every moment where the quantum dice rolled differently, produced a version of your life that is running right now in a dimensional reality permanently and fundamentally unreachable, not because it is far away, but because the dimension separating you from it has no direction in our universe, and no distance that any instrument could ever close. Number 1. The dimension of time. What physics reveals is already behind you. Of all the dimensions physics has proposed, only one is beyond any serious scientific dispute. We do not need to theorize about it or search for its signature in laboratory experiments. We experience it directly, continuously, without the ability to stop or reverse. Time is the one dimension every conscious being navigates without choice. It is also, as more than a century of increasingly precise physics has revealed, the dimension we understand least, the one whose true nature contradicts our experience most completely, and the one whose actual contents may be the most disturbing thing in this entire list. In 1905, Albert Einstein's special theory of relativity established that time is not a background against which events occur, but a genuine dimension, fully equivalent to the three spatial dimensions, united with them into a four-dimensional structure called spacetime. In 1908, mathematician Hermann Minkowski formalized this into what physicists now call the block universe, a model in which all moments in time, past, present, and future, exist simultaneously and permanently as fixed locations in four-dimensional spacetime. In this picture, the past does not cease to exist when we leave it. It continues to exist, exactly as it was, at its location in the four-dimensional structure of reality. Nothing in the equations of relativity makes the past disappear. It simply becomes inaccessible as we move forward through time. Every fundamental law of physics is time-symmetric. The equations of quantum mechanics, electromagnetism, and general relativity all work identically, whether time runs forward or backward. There is no preferred direction in the laws themselves. The one-way flow of time that every human being experiences, the sense that the past is fixed and the future is open, appears nowhere in the fundamental equations. It emerges, physicists believe, entirely from the second law of thermodynamics, the tendency of systems to move from ordered states to disordered ones. The arrow of time is not written into the laws of physics. It is a statistical property of a universe that started, for reasons not yet understood, in an extraordinarily low entropy state. Carlo Rovelli of the Centre de Physique Théorique in Marseille has argued in papers including his 2009 essay, Forget Time, that time may not exist at the fundamental level of physics at all, that it is an emergent phenomenon, like temperature or pressure, arising from the collective behavior of matter, rather than being a property of the universe itself. The Wheeler-DeWitt equation, which represents the most serious attempt to unite quantum mechanics with general relativity into a theory of quantum gravity, contains no time variable. Time does not appear in the equation that is supposed to describe the most fundamental level of physical reality. Sean Carroll of Caltech and his colleague Jennifer Chen proposed in 2004 that the asymmetry of time requires the existence of a larger structure, a multiverse in which our Big Bang was a low entropy branching point, with another universe extending in the temporal direction we call the past, its inhabitants experiencing time flowing in the direction we call backward, each universe as real as the other, each permanently invisible to the other. You cannot visit the past, not because it does not exist, but because the dimension separating you from it runs in a direction your body cannot turn. Every moment you have ever lived, every conversation, every face, every version of yourself from every earlier year is still there, fixed and permanent, at its location in the four-dimensional block of spacetime, exactly as real as this moment, exactly as real as you are right now, in a dimension you have already traveled through and can never enter again. If you want to see more videos like this, click the video on screen now and make sure to subscribe.